Now that we can do an electron configuration for any of the elements, and now that we understand a little bit about how the periodic table is laid out according to the electronic structure, we can start getting information from our electronic structure. We can start getting information from the periodic table. The periodic table is a wonderful cheat sheet. It will help us to find out so much information about how the elements behave, both chemically as well as physically. So we're going to be looking at the trends of the size of the atoms in this lesson, and we're going to be looking at something called effective nuclear charge, because it's this effective nuclear charge that drives the property of size and many other properties of the elements. All right, so how do we measure the size of an atom? We look at something called the atomic radius. So the atomic radius is defined as 1/2 the distance between the nuclei of adjacent atoms. So I have two examples shown here on the screen. On the left we have something that's a non-bond. There's not a chemical bond between them, and we've solidified it. Maybe it is a metal crystal to where one metal atom is sitting next to the next one metal atom is sitting next to the next metal atom. And to measure the radius, a lot of times, you know, when we think about a radius of a circle, we measure from here to here, and we decide on that radius. But that is not a measurement we can make. The electrons, remember, they take up such a tiny, 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 tiny portion of the space there, and you can't find that outside boundary. But if you have two of them together, and we have the nucleus here, and we measure that distance, a nucleus can be identified and found. We can bombard it and hit a nucleus and know where that nucleus is because it's highly dense, packed protons and neutrons. So if we can find those two, we can measure that distance, and 1/2 that distance would be the radius of the atom. Now, if we have the actual chemical bond, which is what we have represented on the right, a covalent bond, then 1/2 the covalent radius from one nucleus to the other would be the atomic radius. So when we talk about the size of atoms or the size of ions, you just need to be aware that that is how they are making those measurements. Now, here is the trend. We're going to learn the trend, and then we're going to learn how and why the trend is the way it is. As we move to the right on the periodic table, as we're moving across the right on the periodic table, it says that the radius is getting smaller, it's decreasing. So even though as we move across the periodic table, we're getting more and more electrons, we're putting the next electron in, we're getting more and more protons, it's getting smaller as we go to the right. And it's also, well, it is getting larger as we go down any one of these groups. So we see getting larger as we go to the right, down, and we get smaller as we go to the right. And what we need to do is figure out why that would be. So we look at something called the effective nuclear charge. Effective nuclear charge comes from a concept called shielding. And what shielding is the effect in which electrons are feeling that pull of the nucleus. So we know that the nucleus is sitting there with its positive charge, and we know that the electrons are moving around it, so we'll let that represent my nucleus, and we have these electrons out here, okay? The effect in which the electrons, some electrons can reduce the field of another electron on that nucleus. So there's an electron here, there's a nucleus here. This electron can shield that electron from feeling the entire effect of that nucleus. And that's what we call shielding, all right? So this effective nuclear charge is what this electron or any electron is feeling that nucleus as, okay? So that nucleus might have 4 protons in it. And this electron out here might not feel that whole pull of +4. But whatever it is feeling that pull as is what we call the effective nuclear charge. So a nuclear charge is how many protons in there. And we use Z, which is what we use for atomic number. We use Z to represent the real nuclear charge. In this case, it has a Z of 4. The effective nuclear charge is this nuclear charge minus what the shielding occurs, okay? So That's what that little sigma is that you see on that screen. The sigma is the shielding, how much electrons are shielding the outer electron from filling that nucleus. So here are different degrees of shielding. Let's look at it here, and we're going to use, an animation here. All right, so here is a nucleus. All right, it's positively charged. We're going to call it a guy, and he's going to have a bow tie. All right, so this girl comes to the party, okay, and this girl is an electron, and we'll put a bow in her hair. Okay, now she's at the party and he's at the party, and she is feeling an attraction for that nucleus because opposites attract. This is an electrostatic attraction. All right, now it says here on the screen that electrons are shielded very effectively by electrons in subshells that are closer. So this girl is feeling an attraction to that nucleus, but along comes another girl to the party. All right, here's the next girl to the party. She is closer to this nucleus. She is going to be blocking her from being able to feel the attractive force that she has for that proton in the nucleus. So this guy would be very effective, this gal would be very effective at shielding her from the nucleus. So doing a good job shielding. All right, that's the first statement. All right, it says here that electrons that are in the same shell are only shielding a little bit. Okay, so we're going to get rid of her. All right, and let's have an electron that's out here equal distance from the nucleus, okay? So they're both there at the party. They both have a pretty equal share of being able to attract the attention of this nucleus. Now they're going to shield each other a little bit because his attentions can be divided. But over here is an electron that's coming to the party and is further away. Now that electron is going to not be effective at all at shielding this electron from the attraction of that nucleus. This electron out here can't shield at all. So we've got three levels of shielding. We have the level of shielding with electrons that are closer. They're very effective at blocking these guys. We have the shielding that is in the same level a little bit, and then we have these guys out here that can't shield at all. So that's the different levels of shielding. And when we consider our sigma, which is this shielding constant, all right, and we're going to come up with a value for that, we're only going to consider the ones that are really effective at it, the ones that are in between an outer electron and its nucleus. We're going to compare how effective nuclear charge affects the size by comparing lithium with beryllium. Okay, so let us find them on the periodic table. Here is our lithium, okay. It has 3 protons and it would have 3 electrons. And here is beryllium with 4 protons and 4 electrons. So let's look at kind of me drawing out how that works. Okay, so here's my nucleus. 4 protons in the nucleus. We know for lithium, and that's what we're drawing right now, we know for lithium the electron configuration is 1s2, 2s1. So I'm going to put those 2 electrons in the first shell. Okay, so this is the 1s shell. It has 2 electrons in it. And then I'm going to go out a little bit further out here. And I'm going, sorry, I said that had 4. We're going to correct that right now. It has 3, and I'll let you fix that in your notes. It has 3 protons, it has 3 electrons. We put the first 2 electrons in, and now the last electron is going to go out here. So that is kind of a representation. It's kind of one-dimensional there. It's two-dimensional. Two-dimensional there. But we have this sphere shape right here with 2 electrons in it, and we move a little further out into the 2s sphere, and we have that 1 electron. So what I want to do is determine what we call the effective nuclear charge of the outer electron. What is it feeling that nucleus as? And how it feels that nucleus will affect its location. So if it gets tugged really tightly, it gets smaller. If it doesn't feel it very much, it's fluffed out, it's bigger. So that's what defines the size, and that very often is a challenge for students to understand. They think you put more electrons in, it's got to get bigger because it's got to make room for those electrons. So you put more electrons in, it should get bigger. You put more electrons in, it should get bigger. And that's not what happens. As we move across the periodic table and start putting more electrons in, it's actually getting smaller. And the reason it's getting smaller is because of how this outer electron is feeling that tug of that positive charge. Remember, our idea of how big the atom is versus how small the electrons are, it's like taking that football stadium, having a marble above football's 50-yard line, okay, we got that marble there, that's the nucleus. The rest of Commonwealth Stadium is for those electrons that are even smaller than that marble to run around in. So it's never a crowding issue, it's always an attraction issue. Okay, so we're ready to get the value for this. The effective nuclear charge is the nuclear charge, which is 3, minus the shielding constant. And we're going to do just a rough estimate of the shielding constant. Any electron between this outer electron and the nucleus is going to have a value for that shielding constant. So there are 2 electrons between the outer electron and the nucleus. Okay, because these electrons can move anywhere around in here. Don't think about this one not being in between it. It is in an inner shell. So any electron in an inner shell closer to the nucleus than this will shield it. So we will shield it by a shielding constant of 2. I'm getting a 2 from those 2 electrons. And that is going to give me an effective nuclear charge of 1. So this electron is not feeling a pull of a +3. It is feeling a pull of a +1, and it gives it a certain size. So now let's go to beryllium. Beryllium has 4 protons in the nucleus, and its electron configuration is 1s2, 2s2. So we have our nucleus with its 4 protons, so I will draw my nucleus with my 4 protons, okay? And then we have the 1s shell, and it has 2 electrons in it. And then we have the 2s shell, and it's got its 2 electrons in it. And this is beryllium, and we're trying to do its effective nuclear charge. So Z effective for this guy would be the nuclear charge, which is 4, minus the shielding constant, and the shielding are any electrons between this electron and the nucleus. So we won't worry about electrons that are in the same shell. We will only worry about electrons that are in an inner shell. So this would be -2, and this would be an effective nuclear charge of 2. So this electron is feeling a pull of a +4. And that is going to pull it more tightly in towards that nucleus, and that's why beryllium is smaller than lithium. And as we move across the periodic table, and let's look at it closely here, as we move across the periodic table, we keep putting additional protons in the nucleus. But those electrons are all going in the same shell. So let's consider nitrogen for a moment. Its electron configuration is 1s2, 2s2, 2p3. All of those electrons are in the same shell. They are about the same distance away from the nucleus. They are not shielding each other. It's only these 2 electrons right here that are shielding. So if we wanted to do the effective nuclear charge of one of those outer shell electrons for nitrogen, Z effective would be the nuclear charge of 7 minus the inner electrons, -2. So it would have an effective nuclear charge of 5. So any one of these outer electrons in this outer shell would feel a +5 pull, and it would make it smaller than anything else. So as we're moving across, the Z increases. That's what's happening across there. But the shielding is constant. Now this is true for the representative elements, the big boxes on both sides, here and here. Something different is going to be happening across the transition metal area that we will look at later. Here is a plot where we're increasing the atomic number across the bottom, and the radius is being plotted along here. Now let's look at that first or that second period. Lithium, which I drew on the screen there, lithium is here, and it keeps getting smaller as we move across to neon. Okay, and sodium is here, and it gets smaller as we move across to argon. Potassium is here, and we see that decrease. Now something is happening right here. That's the transition metal area. This is my representative from here to here and here to here. That's the transition. So it flattens out a little bit in the transition metal area. But if we're looking at the next period, we have rubidium down and then on down to there, and a kind of a flattening out period in that spot. So we're going to look at why these transition metals level out. So as we look at this transition metal area, let's compare a couple different elements, okay? We're going to compare scandium and titanium in a similar way that we did lithium and beryllium. But these are two transition elements, so let's pull up the periodic table. Let's find them. These are Sc here and Ti there, okay? And we're going to do their electron configuration. Well, let's do it here on the screen. Sc's electron configuration, we find the noble gas before it, is argon. And then we come down here, 1, 2, 3, 4, 4s2, 1, 2, over 1, that's 3d1. All right, and then we'll do, well, pooey, what did I do? There we go. We'll do titanium. Okay, titanium would be argon, 4s2, 3d2. All right, so let's do their shielding constants on the screen here. We've got a nuclear charge for scandium of 21, okay? Z effective would be the nuclear charge of 21 minus the shielding, sigma. We have to figure out the shielding. Well, with the electron configuration written out there, what we have to realize is the outer shell is the 4s electrons. That's the farthest out. And those 3Ds, they are in an inner shell, even though they're written second. So even though they're written after the 4s, they have a lower N. A lower N means they are closer to the nucleus. Remember, N tells me the general distance from the nucleus, and so they're closer in. So you've got the argon inner core, and that has, if you look at the electron configuration, or the electrons of argon have 18, plus that one that's a D, that's 19. So we're going to have 19 shielding those 4s electrons from filling the nucleus. And that gives me effective nuclear charge of 2. So we have an effective nuclear charge for those 4s electrons. The electrons that are in the 4s are filling a pull of a +2, and that's defining its size. Now if we go to, this was for scandium, Sc, there we go, Sc. That doesn't look good. Sc. All right, big S, little c. Now if we do it for the next one, which is titanium. All right, the Z effective would be the nuclear charge. We look at it on the periodic table and we see that it has 22 protons in the nucleus. And then we're going to subtract out the shielding. Now who's shielding? We've got the inner shell of the argon, okay, and plus we've got the electrons that are in the D subshell. So argon is 18 plus the 2 more. That's 18, 19, 20. So we're going to subtract 20. What are the 2 more? The 2 more are those Ds. So we're know that those Ds are also between the 4s and the nucleus, so they're shielding. All of the electrons up through argon are shielding, plus the 2 more that are in the D, and this is going to give me effective nuclear charge of 2. So these electrons that are in the 4s, and I called it, in the 4s, it's still the 4s2, are filling a +2 pull to the nucleus, and so it's not changing. Now, that is why, if we looked at that table again, it is leveling off. Now, is it exactly flat? No, this is a rough estimate of what's going on in here. But that is why we see a flattening out that occurs. So when we say, as you move across the periodic table, the radius decreases. Okay, this is very true for the representative elements, but it levels off for the transition elements. Now, a lot of times you'll be asked on a test or in your homework, you'll be given 2 atoms and say which one's got the larger or which one has the smaller atomic radius. You might be asked which one, rank them in order of increasing atomic radius or rank them in order of decreasing atomic radius. you can use the flat out trends that you learned. It gets smaller as you move across, it gets smaller as you go up, or larger as you go down, however you want to think about it. That is, the periodic table is laid out in such a way. If the question went one step further and said, why is beryllium smaller than lithium? The answer is not because it falls to the right on the periodic table. That's not a why. That's a trend that helps us to quick and easy see who's larger and who's smaller. But if you want to get down to the why, you've got to get down into the atom and think about the effective nuclear charge and explain what's happening with that in order to determine the why, as one will be smaller than another. Now, as we go down a family, it always gets bigger. As we go down any group, it's getting bigger and bigger, because what happens as we go down is we're putting another inner core in. So we've filled up a shell when we get over to the noble gases, and now we're putting it into the next shell out, and that whole group starts being shielding for those outer electrons, and it will always get larger because you've added a whole bunch more shielding between the nucleus and that outer shell. Okay. I think that's it. Okay, so we've got our idea of the trend. You ought to know the trend of atomic radius. We've got the idea as to why the trend is happening, because we can study and talk about the effective nuclear charge being the nuclear charge minus the shielding, and we know who does the shielding.